Chapter 13 covers the normal distribution. This is a famous distribution. If you've ever heard of the bell-shaped curve or a bell curve, that is the normal distribution. So before we think about this specific distribution, we're going to discuss the notion of describing a distribution of values with a smooth curve. So far we've pictured distributions with pictures such as a histogram. So let's picture a relative frequency histogram of our class height distribution that we've been working with. The bin width, that is how wide the interval is that creates the bars on the histogram, is set to 3 in the first picture, then 2, then 1. So let's take a look at the first picture. It's relative frequency. You can see that on the vertical axis we have proportions on the side. So that means the height of this tallest bar is a little bit less than 0.3 or 30%, so a little bit less than 30% of the class is between 64 and 67 inches. And remember, this is relative frequency, so the heights of the bars are going to add up to 1 because these are in decimal form. So they're going to add to 1. Notice in the second picture we can bend together 2 inches at a time instead of 3 inches. Notice that this bar we picked went from 64 to 67 inches in height. Now we're doing 2 inches at a time. So our bar goes from 63 to 65, and the next one's 65 to 67, and so on. So the bars get skinnier. Notice it's still relative frequency. The values go between 0 and 1 on the decimal scale. And the heights of the bars, again, should add up to 1. And again, we can go down to 1 inch in each bin. And that's our picture on the very right over here. When we do 1 inch intervals, we've got lots of bars, lots more than we had over here. And notice in this first picture, it's like a stair step, very clunky. But as we squeeze down the bin width, it gets smoother and smoother. There's less of these jagged corners to cut off right here. So we could start to see a smooth curve overlaying this distribution. What would happen if we could measure out everyone's height out to tons and tons of decimal places? We could squeeze these bin widths down on the right smaller and smaller and smaller. That's exactly what we're going to imagine when we think about a continuous distribution. Once we put these bin widths down to essentially 0, we're going to cut off these corners because every time it's going to become less and less jagged and it's going to look more and more smooth. So that's exactly what we're going to imagine when we think about smoothing a distribution by overlaying a smooth curve. So let's go ahead and picture what it would look like to draw a smooth curve to describe our class height distribution. It could look something like that. And I would imagine if we measured with lots of accuracy, it would get smoother and smoother. In a relative frequency histogram, if we added up the heights of all the bars, what would the total be? Again, it's 1 or 100. The proportion of observations in any given interval of values is the area under the curve within that interval. So the total area under the curve should equal 1 if we're putting it on the decimal scale or the fraction scale. Now, let's take a minute to let this one absorb. So if I asked you to tell me what % of students in this class were less than 65 inches, all you'd have to do is look at this histogram. Everything to the left of 65 inches, and you'd add up the heights of these bars. About 10% there, 8% there, a little bit more there, etc. And once you add up the heights of those bars, you could tell me the % of students that have height less than 65 inches. We're going to think about this in the same way when we think about area under the smooth curve. The area to the left of a certain value on our histogram We know how to handle that because those are rectangles. To actually find the actual area under a curve, you need to use calculus. But don't worry, you didn't need that for this class. We'll always give you a chart or table of areas if you have to compute an area under a smooth curve. But we want to always think about a smooth curve starting as a histogram, where we squeeze those bars down to size essentially 0, and we've just overlaid the histogram with a smooth curve. Once we smooth a histogram with a curve that has area 1 under it, we're going to call this a density curve. Now, whenever we think about distributions, we want to be able to describe them by describing the center and the spread, and also the shape of the distribution. But let's revisit the center of a distribution and think about it when we're talking about a density curve rather than a histogram. The mean and the median have the same interpretations as they did previously when we were studying histograms. The median has 50% to the left and 50% to the right. So we call this the equal areas point. And the mean is the balancing point. On a symmetric curve, the mean approximately equals the median. They both lie at the center of the curve. We talked about this in the last chapter. That's because when you have a symmetric curve, 50% is to the left, 50% is to the right, and they're equally spaced. So that's the median in the center. It's also the balancing point, so it's also the mean. On a skewed curve, the mean is pulled away from the median in the direction of the long tail. These are the pictures that we drew at the end of Chapter 12 lecture notes. These are the same pictures, and we're just reminding you of them now. Remember, the mean is the balancing point, so in a right-skewed distribution, like the one in picture B here on your paper, the mean has to move to the right to balance the distribution because that long right tail would tip the seesaw in that direction. Here's another little illustration from your book demonstrating what it looks like for the mean to be the balancing point in the distribution. So, a density curve is a smoothed histogram which has area 1 under it, because since the bars on a histogram, on a relative frequency histogram, should add up to 1, corresponding to the area, then so should the area under a smoothed density curve. So the area under the density curve is 1. Now we're going to talk about a special density curve called the normal distribution. The normal distribution is a unimodal and symmetric and hence bell-shaped distribution. This distribution is determined by the mean mu and the standard deviation sigma. The mean mu controls the center and the standard deviation sigma controls the spread. Notice that we're using Greek letters for the mean and the standard deviation. We're using the lowercase mu for the mean and the little sigma for the standard deviation. Previously, we called the mean x bar and the standard deviation s. So why all of a sudden are we calling these Greek letters instead of x bar and s? Well, that's because when we smooth a histogram, we're no longer thinking about having just a sample of observations. We're thinking that we understand having the whole population of observations. So mu, the mean, is actually a population mean. We're thinking about not just having a sample, we're thinking that we know all of the observations in the whole population. And sigma, accordingly, is the population standard deviation. So the sample mean x bar estimates the population mean mu, and the sample standard deviation s estimates the population standard deviation sigma. So the mean mu controls the center. The standard deviation sigma controls the spread. So let's take a look at a picture of the normal distribution with the mean and the standard deviation drawn in. The mean mu is right at the center of the distribution. This is the line of symmetry. This is the balancing point in a symmetric distribution. The standard deviation is the horizontal distance from the mean mu to the inflection point on the normal curve. That's where this thing is kind of going downhill here, and it's going uphill here. So frowny face, smiley face. That place where it changes from concave down to concave up is called an inflection point. And the standard deviation sigma goes from the mean over to that inflection point. Here's a little fact that might come in handy one day soon. The mean mu controls the center of the normal distribution, but that also happens to be the median, since this is a symmetric distribution.